Welcome back to All 4C Learning session 30. In previous sessions we discussed how to prepare aryl halides from benzene diazonium salts and from phenols and Hans-Decker method. All these methods we learned. And in this session we are going to learn physical properties of aryl halides. Here few are similarities in their physical properties with alkyl halides and few are much more different. Have a look here how physical properties of aryl halides are going to change with difference with change in halogen atom and with change in number of carbon atoms in aryl group. So first one, aryl halides are colorless liquids with pleasant odor. Pleasant odor means when you inhale that means you are much pleasant, means you want to take one more time, you want to take breathe one more time, you want to inhale one more time. Such type of smelling liquids what we call pleasant odor. So these are colorless liquids with pleasant odor or crystalline solids with characteristic odor. Crystalline solids with characteristic odor. That means their odor is not comparable. We are not supposed to compare with any other one. Just like what is the smell of apple? Apple smell only. Apple smell only, we have to say. What is the smell of banana? Banana smell only. But we are not supposed to compare, right? Just like that, these aryl halides are also having characteristic odor, but they are crystalline solids, either colorless liquids or crystalline solids, either with pleasant odor or characteristic odor. These are means in case of alkyl halides we learn first four members are gases, and particularly fluorides or chlorides are gases, but bromides and iodides are liquids. Generally we discuss like that, but here not like that. All aryl halides are having similar properties like colorless liquids or crystalline solids. Let's come to the second point. Melting and boiling point of aryl halides nearly same as that of alkyl halides, which consists same number of carbon atoms. When both are having same number of carbon atom, both means both alkyl halide and aryl halide. When both are having same number of carbon atoms, then their melting and boiling points are very close. But we cannot say exactly same that melting and boiling points are very close. And boiling point for monohalo aryls or monohalo derivatives, if you observe, fluorides less than chlorides less than bromides less than iodides. That means fluorobenzene, chlorobenzene, bromobenzene and iodobenzene if we compare. In all these things, benzene ring is common, but differ in their size of halogen atom. Fluorides, fluorine is small size compared to that chlorides, and chlorine is small size compared to bromides, and bromine is small size compared to iodides. That means fluorine to chlorine, chlorine to bromine and bromine to iodine, size gradually increases, as we know very well. With increase in size, with increase in atomic weight or molecular weight, van der Waals forces are going to increase. Because of van der Waals forces increases, obviously boiling point increases. Boiling point increases. That means with the same number of carbon atoms for different halogen atoms, with the increase in van der Waals forces, with increase in size, with increase in molecular weight, boiling point increases. We can say like that. For same halogens, let us consider same halogen, all fluorides or all chlorides, all bromides, all iodides, whatever it is. For same halogen, melting and boiling points increases with increase in size of aryl group, or with increase in number of carbon atoms in aromatic ring or side chain, whatever it may be. So for same halogens, boiling point and melting point both increases with increase in size of aryl group. Let us consider boiling point of some aromatic, means isomeric dihalobenzene. I used to consider ortho-dichlorobenzene or 1,2-dichlorobenzene, meta-dichlorobenzene or 1,3-dichlorobenzene, para-dichlorobenzene or 1,4-dichlorobenzene. So in all these things, all these three rings are benzene rings only, but here are two chlorines, here also two chlorines, here also two chlorines. But how these three are differ? All these three are isomers. Which isomers? Positional isomers. In one isomer, both chlorine atoms are located in first and second position. In second isomer, 1 and 3. In third isomer, 1 and 4. That means Here boiling points and melting points, how they are going to vary? If you observe, boiling point of orthodichlorobenzene 453 Kelvin, whereas metadichlorobenzene 446. That means boiling point decreases, and in this case para 448. That means boiling point of isomeric dihalobenzenes generally ortho is greater than 453 is greater than para is greater than meta. Why boiling points order like this? Why ortho greater than, para greater than, meta? Even though all these are having same molecular weight, why these differ like that? But the variation, if you observe, that is very less. Variation is very less. 453 to 446 7 and 446 to 448 only 2 Kelvin. That means we can say here meta and para almost close to each other, and ortho is little bit more. So we'll discuss why like that. And let us check out the melting point also. Melting point, para isomer is greater than, para how much? 325 Kelvin greater than, ortho 256. There will be a huge difference. Earlier in boiling points, the difference from ortho to para and para to meta, that the variation is very small, means very less difference. Whereas in this case, melting points, huge difference. If ortho is 256, para is 325 Kelvin and meta is 249 Kelvin. So why this much variation in melting points, and why not that much variation in boiling points? And why boiling points are going to vary from ortho to meta and the meta to para? What is the reason behind it? Let us have a look here. Mainly, boiling points depending upon intermolecular forces. Here intermolecular forces again, in which case intermolecular forces are very high, in which case intermolecular forces are very less, that we need to think. So in all these cases, even though same benzene ring and 2 chlorine atoms, in ortho, meta and para, because of intermolecular forces mainly depending upon the dipole moments, Here van der Waals forces same because of same molecular weight, and molecular size almost really close because of this one here. Both the Cl atoms are very close to each other. Here little bit large, and here somewhat maximum distance they are maintaining. So size wise there will be a small difference. That's why we can say boiling point small difference. Size wise they are not going to occupy same area. That's why there will be a difference in their boiling point. And the second one, boiling point, we can explain based upon intermolecular forces. Here in this example, intermolecular forces, not only van der Waals forces but also dipole-dipole interactions. The dipole-dipole interactions we will discuss in last point. And let us come to melting point. Melting point not only depending upon intermolecular forces but also depends upon crystal structures or symmetry in their structure. I am repeating once again, melting points not only depends upon intermolecular forces. In addition to that, which symmetry it is going to maintain. For example, assume here if we consider this is a box. In this box, if we are going to place the orthodichlorobenzene or metadichlorobenzene molecules like that. So orthodichlorobenzene, this much area it is going to occupy, and within this area one more molecule may not approach. Means here when you are arranging the molecules one after another, there will be a huge gap in between two molecules of orthodichlorobenzene. Whereas when you come to meta, here also that symmetry is not there. That's why in between two molecules some space left. And whereas in case of para, because of symmetry, within a unit area, the number of molecules which can accommodate within one unit area, that will be more. I am repeating once again. Because of symmetrical structure of para-dichlorobenzene, here what happened? More number of molecules we can place within one square centimeter or 1 square meter area. That means more packing is possible. I am repeating. In solids, melting point is for solids. In solids, they can pack much more close. In case of para, dichloro, much more close. That's why. Because of close packing. Why close packing? Because of symmetrical structure. close packing is possible. Because of close packing, within 1 square centimeter or 1 square meter area, more number of molecules we can place that. That means more intermolecular forces. That means we need to provide more amount of energy to break that intermolecular forces. Hence, if you observe, for ortho and para, particularly compared to ortho and para, ortho and meta, para isomer has a more melting point. But the same melting point, if you observe 249, 256 means variation is very less. So for only para, variation is very high. That means compared to ortho and meta, para isomer has more melting point because of symmetrical structure and close packing. And in case of ortho and para, such close packing or packing efficiency compared to meta is less. Packing efficiency means again within 1 square centimeter area or 1 square meter area, how many molecules we can place. That is less because of unsymmetrical structure. Hence, their melting points relatively less compared to para dichlorobenzene. Now, so melting point and boiling points order for same isomeric dihalobenzene, if you observe, ortho is greater than meta, para is greater than meta in case of boiling point, whereas in case of melting point, para is more than, ortho is more than meta. Here difference from ortho to meta is very less, and here difference in all these three also very less. Let's come to next point. Being organic compounds, these are insoluble in water. Means aryl halides are insoluble in water, but soluble in organic solvents. Because like dissolves like principle, based upon like dissolves like principle, covalent compounds preferably soluble in covalent solvents. So organic solvents, hence aryl halides also completely miscible with organic solvents, but the same aryl halides is not going to dissolve in water. And previous session we have learned that for preparation of so many aromatic compounds, generally we are going to use benzene diazonium chloride (BDC). That BDC is soluble in water and also in polar or non-polar solvents, means organic solvents. It can miscible with both, but here aryl halides is immiscible with water, but miscible with only covalent compounds, means covalent solvents, means organic solvents. Aryl halides are heavier than water. Obviously, aryl halides are heavier than water, and in case of alkyl halides, again we discussed one more point. Whereas in case of fluorides and chlorides are less heavier than water, means lighter than water. Fluorides and chlorides are lighter than water, whereas bromides and iodides are heavier than water in case of monohaloalkanes. In case of monohaloalkanes, in case of alkyl halides, we learned one point. If alkane is monohaloalkane, that also, if that monohalo group is fluorine or chlorine, in case of that compounds are lighter than water. That means which floats on water. Whereas if it is a bromide and iodide, then obviously denser than water. That means water floats on that. But here aryl halides not like that. All aryl halides are heavier than water, denser than water. Means when you mix these two, water floats on these liquids. Heavier than water, and density of aryl halides increases with increase in atomic weight of halogen or with increase in molecular weight of aryl halides. Density of aryl halides increases with increase in atomic weight of individual halogen atom or overall molecular weight of aryl halides. So, aryl iodides are more denser than aryl bromides than aryl chlorides. Iodides have more denser than bromides, and bromides are more denser than chlorides. Let's come to dipole moment. As we know, the dipole moment is nothing but mu is equal to del into L. It is a product of charge upon any one pole and distance between two poles. Dipole moment is the product of charge which appear upon any one pole, that indicates with del, and distance between two poles, that is indicated with L. So mu is nothing but del into L. You should remember one point. That is, dipole moment not only depending upon charge, not only depending upon distance between two poles, it is the product of both. Have a look here. In case of fluorobenzene, chlorobenzene, bromobenzene, iodobenzene. In case of fluorobenzene, what we are expecting? So because of fluorine is more electronegative, it pulls that sigma bond electrons towards itself more, resulting more and more negative charge developed upon this fluorine. And in case of chlorine, less electronegative, and moreover you mentioned that plus sum effect. Because of plus sum effect, something happened here. So the negative charge what developed upon this chlorine is less, and the same we are not expecting that much in case of bromine, and in case of iodine much more less. That means the dipoles what created upon particular halogen atom is less in case of iodine, and it is very high in case of fluorine. So generally what we think, because of more electronegative, it pulls electron towards itself, and so more delta value, dipole moment of fluorobenzene is more in general we are expecting. But let us see the experimental value. For fluorobenzene it is 1.60 dBA. 1.60 dBA. So compared to fluorobenzene, what you are expecting for chlorobenzene? So because of compared to fluorine large size, less electronegative, its tendency to pull the bond pair of electron towards itself obviously less, hence the partial negative charge which developed upon particular chlorine atom also less, hence del value is less. That's why mu value is less. Generally this is our expectation, but it is not our, that expectation was wrong. So if you observe it here, 1.69 dBA. For fluorobenzene it is 1.60 dBA. For chlorobenzene it is 1.69 dBA, which indicates that dipole moment of fluorobenzene is less than chlorobenzene. Let us go for bromo and iodobenzene. For bromo and iodobenzene it is very close to 1.70. So here 1.69, 1.70, that variation is very small, but 1.60 to 1.69, that variation we need to consider. Means considerable difference is there from fluorobenzene to chlorobenzene, but from chlorobenzene to bromobenzene and iodobenzene, considerable difference is not there. So if our explanation only based upon that electronegativity concept, if it is true, then it should correlate with the experimental values, but the experimental values are completely different from our explanation. So we are not supposed to consider dipole moment means not only charge, but also we need to consider length, means distance between two poles. Here in case of fluorobenzene, even though del value is more, because of fluorine size is small, because of fluorine small size, distance between these two poles means F and carbon, ring containing carbon, that distance is small. I am repeating once again, even though fluorine is more electronegative, upon fluorine more negative charge developed, that accepted. Whatever we explained earlier, that is true. But dipole moment is not only depending upon that del value, it depends upon one more factor, that is distance. That distance mainly depends upon size. Here let's come to that explanation. In case of fluorine, because of small size, CF bond length or bond distance means distance between two poles means L value is less, even though del value is more. L value is less. That's why the product of del into L value remains as 1.60. Whereas when it comes to chlorobenzene, even though here chlorine is less electronegative compared to fluorine, even though its ability or its tendency to pull that bond pair of electrons is less when compared to fluorine, but because of chlorine large size, Cl bond length is more, that means L value is more. Because of more L value, what we say, del into L value comes to 1.69 dBA. So here for fluorobenzene it is 1.60 and for chlorobenzene 1.69. Why dipole moment of fluorobenzene is less than chlorobenzene? Not because of del value. Del value obviously more for F, no doubt that one. But because of L value, distance between two poles is more for CCl than CF. That's why dipole moment not only depends upon del but also depends upon L. So it is whole del into L. So the product, which case the product is more, for the dipole moment is more. And in case of bromine and iodine, even though size increases, even though increase in size, we are expecting because of from fluorine to chlorine, because of increase in size, mu value increases, dipole moment value increases. So from chlorine to bromine again size increases, from bromine to iodine again size increases because of increase in size. What we are expecting? Mu value further more and more, but not happen. It remains same, means chloro to bromo, bromo to iodo. That variation is not considerable because the increase in size is compensated by decrease in electronegativity. The increase in size is compensated by decrease in electronegativity. That's why fluorobenzene dipole moment is less than chlorobenzene, chlorobenzene is less than bromo, almost similar to iodo. This is dipole moment concept. So if we are going to consider dihalobenzenes. So as we learned that there are three isomers as possible, ortho, meta and para, of which whose dipole moment is more. As we learned in previous classes, as dipole moment is nothing but a vector sum. Vector sum. If mu1 is one bond moment and mu2 is another bond moment, by merging these two, net bond moment will be vector sum, that is nothing but resultant is equal to mu1 square plus mu2 square plus 2 mu1 mu2 cos theta under root. So this is the vector sum. If mu1 is one bond moment and mu2 is another bond moment, and net bond moment, dipole moment is square root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Let's see here. In case of para-dichlorobenzene, dipole moment is 0. Why like that? So for these two explanations. Here CCl bond, this one is pulling towards itself and this Cl is pulling towards itself. These two are pulling in opposite direction. Here this is vector direction and this is vector direction. Both are same magnitude. Net dipole moment cancels each other. In other words, they apply the same principle. So mu is equal to under root, say CCl bond moment is a mu, because here also CCl, here also CCl, both are same. So that's why mu1, mu2 not necessary. Either of these two, say its bond moment is mu1, okay. This one is mu1, obviously this one also mu1. So net is equal to mu1 square plus mu2 square means again mu1 square plus 2 mu1 mu1 mu2 means mu1 again mu1, both are same. Mu1 mu2 cos theta cos 180. So this mu1 square plus mu1 square 2 mu1 square. This is 2 into mu1 into mu1 2 mu1 square cos 180. It will be minus. Total will be 0. So net dipole moment is 0 for this one. Para-dichlorobenzene net dipole moment is 0 because of here the both dipoles are net cancel each other, are both are same atoms. Net vector addition mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. If you substitute that cos theta, theta value is 180, then obviously it will be 0. Let us apply for the same meta ortho-dichlorobenzene. In case of ortho-dichlorobenzene, here the bond angle is 60. In between two chlorine atoms, bond angle is 60. Let us assume this one again mu1 and this one also mu1 because of both are same atoms. So in such a case mu1 square plus 2 mu1 into mu1, here cos 60 as you know very well 1 by 2. So if you apply, you are getting 2.54. Remember that cos 60 means mu1 square plus 2 mu1 means 2 mu1 square cos 1 by 2. So again mu1 square, right? It overall root over 3 mu1 square, 2 mu1 square plus mu1 square. So root 3 mu1 square, that value 2.54, remember that. And when it comes to meta position, in case of meta, bond angle is 120. Bond angle is 120. That means net dipole moment mu is equal to mu1 square means this CCl bond moment and mu2 square, another mu2 means again mu1 because of that also CCl. So mu1 square plus 2 mu1 into mu1 means 2 mu1 square cos 120. Cos 120 means again cos 90 plus 30. Cos 90 plus 30 means minus sin 30. So here net vector sum mu1 square plus mu1 square means 2 mu1 square minus, you are doing what? Minus, you are subtracting something. That's why its value decreases 1.72. Hope you got the point here. Dipole moments we need to consider bond moment. That bond moment, how it is? In case of para-dichlorobenzene, angle is 180. Because of angle is 180, net vector sum will be 0. And in case of ortho-dichlorobenzene, what happened? Net vector sum is not 0 because of angle is 60, cos 60 is 1 by 2. So if you substitute that, 2 mu 1 square plus something you are getting. Whereas when it comes to meta, 2 mu 1 square plus 2 mu 1 square cos 120. Cos 120 is cos 90 plus 30, which means minus sin 30. So you need to subtract this term. So ultimately dipole moment decreases. Now ortho, meta and para, for all these, dipole moment of ortho is greater than, meta is greater than para in case of dichlorobenzenes. Now physical properties of aryl halides is one, and we need to enter into chemical properties. That chemical properties of aryl halides are completely different from alkyl halides.